Hello. Um, Upon a question from discourse, I remember that I promised, um, considering exercise 2.1a, the expected value for the estimate of parameter a hat. I forgot about it. I am sorry about that. And I'm preparing this Pencast to explain how this expected value for the estimate is found. Of course, for the least squares estimator, we actually don't need to consider the noise properties to come up with the least squares estimator. However, once we have information about how this noise is distributed, we can actually analyze how our least squares estimator behaves. So we can calculate the expected value and variance. By calculating the expected value, we can see if the least squares estimator is biased or not. And we can calculate the variance and compare it to Cramer-Rao lower bound. So it's perfectly doable. But again, you don't need to know anything about noise to come up with the least squares estimator. Once you have information about how noise is distributed, you can analyze the least squares estimator. And this is exactly what's happening here. So I'm not going to derive the least squares estimate, the a hat. I will just continue from the expression for a hat once you solve, minimize the squared error term. So what we have is the a hat is equal to, it's a summation of terms from 0 to n minus 1. And we have our data points, which are normalized by the noise variance in this problem. So it's a weighted least squares problem. And this is again divided by inverse of the noise variance. Okay. Now, we are interested in the expected value for a hat. To calculate this, we need to keep in mind two very important properties for the expected value. I'm going to note them down here and say we have two random variables, a and b. And if we have the expected value for some of these two random variables, we have actually some of the expected values for these random variables. And second property, so this is the first one, the second property, we have the expected value of the random variable multiplied by a deterministic, that's important, deterministic coefficient. In that case, that deterministic coefficient just comes right out of the expected value operation. And this is what we have in the end. Now, let's go back to a hat. This complicated looking expression actually consists of a couple of different constituents. Xn is the random variable here, but sigma squared n, that's deterministic. That's a parameter given already in the problem. So when we are dealing with the expected value of a hat, we are dealing with the expected value of this whole expression. In the denominator, there's no data, there's not a single random variable here. So this comes right out of the expected value operation. So you can think about this like we keep the denominator as it is. That's what it means to come right out of the expected value operation. And on the top, we have this summation of different random variables. Using this property 1, we can say that the expected value for this whole expression can actually be written as sum of the expected values. You see? And of course, in the denominator here, we have sigma squared. Again, this is deterministic using second property. The expected value for this whole division turns into the division of the expected value for data by the deterministic parameter sigma squared. And what about the distribution of xn, expected value of xn? Well, xn is given as summation of a deterministic but unknown parameter a and the noise, which is zero mean, uncorrelated, with variance sigma squared. That means we can write this expected value of xn as expected value of signal model with noise. So it's expected value of a plus omega n. I'm not writing it again. It's the same thing. So we are dealing with this one. And the expected value for a deterministic value is the value itself. So expected value of A, is capital A here, is just A. It means I have the summation of A divided by sigma squared n plus summation of omega n, the noise samples, divided by sigma squared n. Oh, sorry, there has to be the expected value here. Yes. And in the denominator, we still have the same stuff. So what happens here? We have the expected value for the noise sample. Remember, it's zero mean. The expected value for the noise is zero. It means the expected value of the estimate is actually, and consider this constant. It's independent of n. It comes right out of the summation term. It is a sum n from 0 to n minus 1 over sigma squared n divided by, this time around I'm going to write it down for dramatic effect, and that's the dramatic effect I'm talking about. Hey, this is an unbiased estimator. The expected value for a hat is equal to a. I hope this clarifies this exercise, and if you have any other questions, please don't hesitate to contact us. Thanks.